so much for the introduction and the opportunity to sort of present our what we've been talking about here now for 3 weeks, and we'll continue up until Christmas in the Active Solids program. I think the spirit of this lunch talk is that it might stimulate discussions with research areas that we are not familiar with, in particular with discussions between the many-body quantum optics and the active solids community. So I encourage you to ask questions, interrupt if anything's unclear. Hopefully there won't be any surprises to the other active solids participants in what I'm going to say, but there's certainly, everybody is welcome to participate in the discussion. So I thought where I could start with this Blackboard talk is to try to define what an active solid is. I think this is an ongoing effort. I don't think there is a well-accepted definition of active solids, but there are certainly examples and models that we've been discussing that we sort of agree fall within this concept. So the full name of our program is Active Solids from Metamaterials to Biological Tissue. I won't be talking so much about either metamaterials nor biological tissue, but it does sort of give you the spirit of the active solids or community and research effort has been to go across both sort of synthetic active solids and biological materials. All right, so I promised to sort of start with trying to define what an active solid is, and it's sort of composed neatly of 2 words that I will define separately. Right? Active refers to active matter, which is a broader research area of non-equilibrium physics. Right, so this will be the red color. And the first sort of models of active matter originated now about 30 years ago in the mid-90s, trying to understand what we now think of as fluid-like states of active matter. So these are, in many ways, fluids that are far from equilibrium, but they're not driven externally far from equilibrium, but rather get their non-equilibrium characters from the behavior of their individual components. Right? They're composed of particles that move themselves in some way. And sort of a simple model of this is if you think about a fluid of particles as a fluid of self-propelled particles. Perhaps the first model is called the V-check model that studied this. And there are now several related models that all rely on having a self-propulsion that's given to each individual particle and some sort of interaction between the particles. And in principle, the self-propulsion direction, which corresponds to some sort of an individual particle velocity, that could be aligned or could be not aligned. And those are 2 different states of matter that perhaps could be described in the same spirit as the spirit of phase transitions and sort of the both at the kind of mean field phase level as well as thinking about fluctuations and hydrodynamics or large-scale flows that these fluids would have. And so in this spirit, perhaps one of the most common techniques that's used in active matter, in addition to sort of numerical simulation of these, is to coarse grain this fluid to think about sort of the emergent collective properties on scales much larger than an individual particle. This is, of course, what we call hydrodynamics in general, but sort of active hydrodynamics differs from usual hydrodynamics from the Navier-Stokes equations, precisely because these particles do not behave like molecules, because they self-propel with let's say for simplicity, with a fixed speed and some sort of variation in the direction of self-propulsion. Right? So even if each individual particle has a fixed speed, if you start to average it out over some sort of a patch, here then you will get a
an average velocity here with the, the degree of alignment telling you about the magnitude of the speed for this patch, and the direction being given as a sort of the average of these directions. V here with respect to some sort of reference frame, and there's usually a natural reference frame. In 1 second, I'll tell you kind of where some of these models originate from, and maybe a useful thing to think about is birds flocking in the sky, right? And there, there's an obvious sort of reference frame, which is the reference frame of the Earth, which all of these birds see. And of course, none of this is frame invariant, right? The frame is an important.
It implies that particle decide by itself where to go.
Mm-hmm.
No, I mean I understand that it is too primitive, but still the word active. So what defines where is self-propelled?
Yeah, how is it self-propelled? So there, I would say that there's perhaps a somewhat of a scale for how active something is, right? Where the activity comes from, but the kind of going all the way from sort of driven to active, right? You can sort of think of that as a scale. And there's clearly systems, I would say, like birds, right, that are clearly sort of self-propelled, right? I mean, they eat food and they store all of this energy, right? And then they do whatever they want, right? And then there are other particles that, for example, are self-propelled due to an external electric field, but they still have, they have some sort of energy input that's instantaneous, but they still have the freedom to decide where they go. And that could be, either purely physical or some combination of physical, and chemical.
This is very active by some kind of intellectual.
Yeah. So to me, no. I would say that there are some cases where active means really having a brain, but other cases it means absolutely no brain, just purely a physical process. And perhaps those are more amenable to physical treatment. All right, so I said that kind of a nice approach to thinking about a model like this is to coarse grain. Right? And of course, we're sort of used to thinking of spins in, let's say, in the plane, right, and coarse graining them to give us an order parameter. And you can think of the same way here, where you have some sort of now an average polarization field, right, where that coarse grains these velocities, and if the particles are self-propelled and their velocities are somewhat aligned, then this polarization field will be non-zero. Right? And so far, this seems somewhat similar between kind of equilibrium spin systems and active matter systems, in the sense that you have a vector-like order parameter. Right? You could think of this as an XY model, but of course, the big difference here is that the polarization also corresponds to the average velocity, right, of these particles. So it's not only that the polarization is zero, but also that the average velocity in the steady state is non-zero, and in fact the two are proportional to each other. So this defines, in many ways, an active fluid. We're used to thinking of fluids in terms of the evolution of their velocity fields, and you can write down equations for this velocity field. I won't do that, in part because I want to move on to sort of solids and how solids might be different from fluids.
What about the fluctuations of these quantities?
Yeah, so the fluctuations of these quantities are indeed important, and it turns out that, for example, one of the first significant results in active matter, I would say the Turner 2 theory, wrote out a kind of a continuum description for this model in terms of the velocity fields, and then showed that you can have long-range order in 2 dimensions, right? Because you are not constrained by equilibrium. You can sort of break what's called the Merman-Wagner theorem that says that the XY model will not have true long-range order, will only have a quasi-long-range order, and show that the velocity field really, somehow the fluctuations in the velocity field are suppressed because of this active non-equilibrium nature.
Can one write a diffusion equation, or
Yeah, so it would be more of it would have an advection diffusion-like character as well as a sort of Landau-like free energy, right, which isn't really a free energy, but rather corresponds to this alignment interaction. So these are all kind of components in a continuum theory for this velocity field. All right, so I promised to get to solids here, and the aspect of solids that's kind of relevant to our program is solid mechanics specifically, right? There's, what we haven't talked about, but perhaps should talk about, I encourage you to talk about, are kind of quantum active solids or any sort of solid state physics, electronic physics that might be relevant to active matter, and instead have been thinking purely about from mechanics and structural mechanics or solid mechanics here. And so solid mechanics has at least two sort of relevant components to it that we've been discussing. One is elasticity, sort of the description of solid deformations at large scales and slow time scales. And the other aspect is sort of phonons and kind of linear excitation beyond the elastic regime. So in particular, if you think about active matter being fluid-like, then solid mechanics is, well, solid-like and elastic-like. So rather than thinking about the velocity fields, you can think about the displacement fields of the solid or the strain fields, and a theory of elasticity and viscoelasticity in particular, if you have something in between a fluid and a solid, seems relevant to any sort of active solid framework. So viscoelasticity. And the other thing I said is sort of phonons or waves. Again, fluctuations now, but now in the solid mechanics field. So I would say that, a very broad definition of active solid is something that combines these two aspects, right? An active matter system where each individual particle consumes energy, and then that energy is could be used for self-propulsion, could be used for deformation of the elasticity field, but in any case, elasticity plays the role of both the communication between these active particles, the fixing them in place relative to each other. In other words, they start to behave like a coherent whole, like a solid-like material. Yeah, so I'll get to examples for this. So I wanted to get to maybe start with examples of why people started thinking about active matter. And, so I mentioned birds as one particular motivation, right? You can think of each individual particle as modeling a bird, modeling the very complex behavior of a bird. And we know that birds align and then flock together, to migrate or to avoid predators. There's really, reasons for this behavior. And similarly with schools of fish and on land, various herd animals, right? And it turns out that while their overall behavior is very complex, right, you would need to somehow take their brain into account. In many ways, they kind of compute things in a very simplified way where a bird looks in its neighborhood, right? They can only see its neighbors in a dense flock, and then says, well, I'm going to follow these neighbors in order to avoid running into them. And it turns out that similar processes are used at the kind of cell and tissue levels, right? Now you think of each particle as a single cell in a collection of cells, and if you want the whole tissue to flow, the whole organ, or for example, a bacterial colony, then to flow, then each individual organism will align with its neighbors. And then finally, there's sort of synthetic examples of these where these are kind of, let's say, microscale particles that are somehow using energy in their environment. This could be light, this could be chemical energy, again, to self-propel. And then often it's, if these are immersed in fluids, they create a flow profile around them. And then this flow profile aligns the neighbors with this particle. All right, so what's an example of an active solid? I'm going to start with a model active solid, a model that's been implemented in experiments that's sort of based on this self-propelled particle system. So I'm going to sort of minimally add solid mechanics to this self-propelled particle model. And the way you can do this, that's maybe, well, a little bit more than just adding springs between the particles, is to take each individual self-propelled particle and confine it in a disk. Let's say this disk, right, is really a wall, but it's a wall that can sort of move if the particle hits it. Right? So it has some sort of low friction with a substrate on which this all sits. Right. This was in fact done with a fairly large self-propelled particle, what's called a hex bug. It's about a couple of centimeters in size in Olivier Dauchot's lab in Paris. And so what happens if you take one of these, let's say in the beginning fix it in space, then the self-propelled particle will sort of go around inside until it hits a wall. And then it will naturally sort of follow this wall. This is sort of one steady state that you can have. And of course, there are sort of two spontaneous directions, two spontaneous chiralities that this particle can pick to go either clockwise or counterclockwise. And the interesting thing to sort of make this into a solid mechanics model is you take several of these sort of caged self-propelled particles and you couple them together elastically. And so you take a spring and another caged particle, this circle worked out less well. And this particle will also, yes, this is purely a two-dimensional model. And okay, so without the spring, right, these two particles would behave completely independently, right, as long as the confinement doesn't run into each other. They would therefore, spontaneously, individually pick their direction, their chiralities for self-propulsion. They would also spontaneously pick their phases, right, where they are in this orbit. You would have, you wouldn't observe any correlation, any sort of collective state. But this turns out that adding the spring here couples these two particles together so they can communicate and synchronize their motion. So this is very much like a synchronization phenomenon. But now this synchronization phenomenon is coupled to the mechanics of this material. And so what they did in the lab was to build a triangular lattice of these particles, right? So now in this triangular lattice, each of the atoms, if you wish, is one of these sort of robot cage complex. And you have a triangular lattice of these. And what they have observed is that not only do the nearest neighbors begin to couple, but also that the entire material picks a collective mode, right? A collective mode where the particles begin to sort of perform an orbit, right? Where the entire material kind of goes around like this. And so perhaps this is a fairly, intuitive phenomenon in that, elasticity allows you to pass information between these active particles, and as a result, they are able to synchronize their motion. But I think it's, yes, please.
Just a quick question about the model. So does the elasticity of the spring, let's say if it's infinitely stiff, does
Yeah, this is a good question. In their case, the spring was fairly weak, fairly stretchy. It was like an elastic filament. So they weren't kind of perfectly synchronized, but it was still good enough. I think if you had very stiff springs, you might, whether they would synchronize better or not, I think is not so obvious to me, and I'm not sure anybody's really explored that. You could imagine that the fact that there's a relative displacement between them also helps with the synchronization.
It's amazing that also the angular momentum synchronizes. I would expect that.
Yeah, so they synchronized. Yeah, they synchronized their phase, right? Which is surprising.
Directions, right?
Yeah, both the direction and.
The direction seems strange.
Well, yeah, I think somehow it's mechanically maybe it's not so obvious, but I guess from the point of view of kind of synchronization of pendula that people have studied for a long time, it's some sort of a complex process that's still.
The string should be able to transfer this kind of correlation between rotation and movement of string, right?
And I think.
Doesn't look simple, right?
No, I don't think it's simple at all, but somehow it does. It does do that. Yeah, please.
So does the spring are only linear network? I mean, the synchronization occurs for the only linear network.
Yeah, exactly. So the springs there are no interactions between, let's say, this particle and this particle. The spring is a very literal kind of elastic spring that they built into the system.
In this experiment, the confinements are soft or are they like rigid circles?
The circles themselves are perfectly rigid. It's only sort of the distance between them that can vary. So one of the reasons that I wanted to bring up this model in experiments is sort of a minimal model of an active solid. You can perhaps make a model that's even slightly more minimal by just saying that, well, I'm going to replace this by a self-propelled particle, one of these particles by a self-propelled particles, and see what happens there. But the kind of maybe more surprising fact about this is that people have also used these kinds of models to understand living systems. Right? So there was there's a lab in Hong Kong, the Yilin Wu's lab, who studies what are called bacterial biofilms. And bacterial biofilms are more or less, abstractly, you can view them in this way, right? Each individual bacterium is like a self-propelled particle. If it's in a fluid, it will sort of form a self-propelled particle state. But in a biofilm, what happens is that the individual bacteria begin to secrete a polymer matrix that then becomes elastic after a while. And there's an interesting period. Eventually, the elastic matrix sort of confines them all, and they lose all activity. But there's an interesting intermediate state where this biofilm is forming, where there's still a lot of self-propulsion in each individual bacterium, but there's enough coupling between the nearest bacteria to be able to synchronize their motion. And that's what they then see in these experiments. So bacterial biofilms in particular are important in terms of applications. They are mostly things you would like to avoid, for example, on when you're cleaning medical devices, right? Bacteria tend to be much more resistant to things like detergents and antibiotics when they're in this biofilm form because the outside matrix protects them. So that's the reason people study them, but it turns out from a purely kind of physics fundamental point of view, a simple model of the biofilm is precisely this one, the self-propelled particles coupled by springs, and the motion that you see in this biofilm state is precisely this one of synchronization, kind of going around like this. Yeah.
So in the end, this simple model mimics well the glassy system where each particle would be trapped in a cage held by the
Yeah.
I was wondering if there's some sort of an equivalent model system for something that would be
Yeah. So that's a very good question. I don't know people who have studied that specific kind of gel-like model. I think that would be really interesting. I would say I don't know of any physical system that behaves more gel-like, but maybe you know some. I think that would be a really interesting question to think about. All right, so this is kind of the first example of an active solid that I wanted to bring up. The other example that's perhaps closer to some of the ideas of non-reciprocity that I know are sort of also of interest in quantum many-body quantum optics is adding mechanical non-reciprocity, right, to active solids. And so if we think about solids as being connected by springs, then we can develop sort of a simple non-reciprocal spring model and then make the solid out of this. And the kind of ideas that this led to we called odd elasticity. Odd both because it's unusual, but also by connection with what is sometimes called odd viscosity or Hall viscosity in quantum Hall systems. Okay, so how do you make a non-reciprocal spring? Well, you start with a spring. And in this spring, you have, let's see, the change in length of the spring will be delta R. There will be a force on this particle, let's say this way, if it's reciprocal due to the change in length of delta R, right? And sort of the Hookean spring law will be that f of delta R is minus k delta R hat, where of course R hat is the kind of the unit vector along the spring. Sort of the simplest kind of generalization or modification of this law that you can make that will immediately take the spring out of equilibrium is to add a force that's not along the spring length, right? So you can always decompose kind of a general two-dimensional force into a horizontal and vertical component here. I'm going to call this component phi hat. And I'm going to add another spring constant that's unrelated to this k. I'll call this the active spring constant. And the force will be still proportional to delta R to kind of give us a linear theory, but now will also be proportional to phi hat. So will be transverse, right, to the direction separating the particles. So perhaps one thing that's not immediately obvious is this is somehow non-equilibrium. And there are a couple of arguments that tell you that it has to be. One is that this clearly violates sort of Newton's third law. Newton's third law tells you that you're not going to create angular momentum in particular. And here, if you take this spring and you, let's say, compress it or extend it, then there will be a net torque, right, between these particles. This particle will want to go this way. This particle will want to go that way. And so the spring will begin to rotate, right? So this violation of the Newton's third law of equal action and reaction we call non-reciprocity in the mechanical context. I would say that just like active solids, maybe the definition, I won't try to give a very precise definition of what non-reciprocity means, but one example of it would be non-reciprocity in terms of Newton's third law. Right, well, why are these things interesting? There's a kind of another example that you can, or as argument that you can give to show that they are active, which is that you can perform a cycle of deformations on the spring that does work on its environment, right? There has to be something in the spring that consumes energy in order for it to do work on something that the spring is coupled to. And so the argument here is that you can start with the spring in its rest length. And now I'm going to extend the spring. I'm going to, let's say, fix the particle here, attach it to a wall, extend the spring. I'm going to redraw it here. Say delta R is greater than 0. And what this will give me is a net force perpendicular to this displacement. And then I'm going to rotate with this force. I'm going to use this transverse force to do work on the environment. I'm going to displace this spring by a certain amount here. And if the initial length of the spring was r, and I displaced it I extended a fairly small amount, then the work that this will do on its environment is phi r delta r times this active spring constant. And the interesting kind of interpretation of this work is that it's precisely the area that's enclosed by this particle that's being moved if you now return it, sort of undo the compression and return it back to the original state, right? This is kind of the network that you will get out after a closed cycle. And so this is equal to Ka times this area in configuration space. All right, so these springs are active, but this is still an individual kind of single particle model. How do we make an active solid out of this? Well, all you have to do is to connect these springs in a lattice again. Yes, please. I think that's a very good question. I think that's a question of sort of active research. So the initial model is certainly purely mechanical, right? But you'd expect interesting things to happen if you include thermal fluctuations in it. But I don't know of anybody who's sort of looked at it systematically. Yes, please.
Sorry, just a basic question which I don't understand. What's the difference if in this I would just have a dynamical system which has some energy and moves, just a particle and eventually bounce off the walls? Would this qualify as an active?
So you're saying this case where this does some sort of complex and
non-linear model of Souslov with kinetic energy and potential energy and interacts with the walls.
so, but you're saying a purely inertial one, so without any sort of friction.
Yeah. Would this be an active particle or not?
I would say not unless you kind of do, keep adding energy to it. For example, it might, start interacting with the walls, pass some of its energy to its neighbor, but then, let's say if you then increase the kinetic energy back here, then I would say it's active. But if you're just talking about a purely, as you say, dynamical system, then, I would say that you wouldn't have this kind of basic ingredient of active matter that a particle continuously consumes energy in order to exhibit its dynamics.
For example, your spring implies that you cannot rotate this shell, but maybe in the reality it could be rotated, right?
Yeah. I think that would be a slightly different model.
It's a little bit kind of symbolic, right?
Yeah. I think this is a particularly simple model, and it's true that there will be certain for example, angular momentum transfer between this and this, and the question is to what degree is that important. There's also, for example, friction with the table in the experiments, and maybe that cancels it out. So I would say that there's certainly connections between dynamical systems, and perhaps some of the tools of dynamical systems that people have used are still very useful to us because, for example, if your particle goes for a long time under inertial dynamics and then gets a little bit of energy boost in between those energy boosts, you can describe it as purely as a dynamical system. But there's something extra here, which is the non-conservation of energy that will always somehow come into the emergent phenomena that we're interested in. Yes, please.
Does elasticity always mean energy input, or can it be purely dissipative? So we were quite used to energy input sounds kind of exotic, but energy output is like decay of energy is fairly familiar. So.
Yeah, it's a very good question. You can certainly drive the spring, right? So if you do the same cycle but in reverse, right, you'll get a negative sign in the work, and then you'll drive the system to dissipate energy into something. I think, again, the definition of an active solid is somehow that the phenomena that we're interested in are precisely those that have to do with energy being done on the environment, or the particles consuming energy. But there again, for example, viscoelasticity, which would be the kind of counterpart to this, that's not active, that's purely dissipative, informs a lot of what we do, right? So it's, I would say, different, but connected to these models. All right. So what happens if you make a lattice out of these particles? Well, here, I'm trying to think if I can just draw a lattice, maybe. So you can ask in the sort of many spring model, right, in the active solid model, what are the consequences of this non-reciprocity in the spring of this extra active force when it comes to a theory of elasticity? And to do that, to write out a theory of elasticity, I'll start out in many ways sort of in parallel to how people usually think about elasticity, which is in terms of stresses and strains. But the key here is that this term can be written in terms of a gradient of a potential, but this term cannot. And that will be true of the active elasticity I write down as well, that it won't be the gradient of any sort of elastic potential energy. Right. So if you take this stress-strain relation in usual elasticity, this tensor describes both the compression and dilation of a solid as well as its shape deformation, so shear. And the stresses kind of correspond to these are the gradients of the stresses are the forces that then correspond to, that arise due to these strains. Right? So both shear and compressional stresses. The proportionality between these two, so they're both rank 2 tensors, so the proportionality will be a rank 4 tensor, which is what we usually call the elastic tensor. And here, there's sort of one conclusion that you can make immediately if you just say that the elastic tensor comes from an equilibrium or a potential theory, which is that if there is an elastic potential, it should have the form of a stress times a strain, or a K-I-J-K-L, U-I-J-U-K-L. I'll keep it in 2 dimensions. And so you immediately see that this elastic tensor will be symmetric under the exchange of these two indices. So breaking this condition, right, that there is no elastic potential energy from which this arises, gives you the opportunity to add a term to this that's purely active that doesn't have this symmetry. So if you have ij k equal k L ij in equilibrium, then the active or odd part of this will have be antisymmetric under this switch in energies, and in principle you can have both of these components for a lattice composed of these non-reciprocal springs. And so here you can then try to think about the kind of analogies with what I said at the microscopic scale, for example, these work cycles, and how you can translate these work cycles into the kind of continuum scale, into the scale of the entire solid. It turns out that you will get a work that will be proportional to an odd elastic modulus, right? So component of this active elastic tensor, and the area enclosed in deformation space, right, in the space of these strains. But I also wanted to say that this, while this again seems like a very abstract model, there have been several experiments that have been done to show that this does occur in both in synthetic and in biological systems. Right? So the three examples that I want to give, there are now others. The first one that's I would say quite surprising, it's by Nikta Fakhri's lab at MIT, where they looked at collections of what are starfish embryos, right? So these are starfish early in their development, and all that these starfish do is that they go to a surface and then begin to rotate around their centers of mass. And in this case, what happens is that their interactions are mostly through the fluid in which they're immersed, right? So you can think of them as kind of a collection of vortices, right, in this fluid, and that means that their interaction is indeed non-reciprocal in that the force law, right, has a transverse component due to the flow field. For example, the flow field on this particle due to this particle will kind of have this vortex-like structure, and therefore a component of the force perpendicular to their separation. That will then also depend on the distance separating them. And so it turns out that the kind of crystals that these starfish embryos form, so they come to a surface, they assemble into fairly large periodic patches of 100 to 200 of these particles. And by imaging these crystals, you can see some of these phenomena associated with non-reciprocal springs. In particular, these starfish embryos are fairly small. They're certainly less than a millimeter in size. The entire crystal is less than a millimeter in size. And that means that they are overdamped. So you do not have inertia, and so you don't expect to see elastic waves. But because you have this odd elasticity, this active modulus that then leads to work cycles, right? You can have a balance between a work cycle that continuously inputs energy into the solid, right? It does work, and the dissipation of energy here. And based on this odd elasticity theory, you can have a prediction for how you expect these waves to propagate in the overdamped system, and then by comparing with experimental data, they were able to extract the values of these odd elastic moduli. In particular, they found that the relative value of the odd elastic modulus to a normal shear modulus, and their system is around 7. So they're really, large, very, very strongly non-reciprocal solids that these starfish embryos form. There's another system that's similar to this at the University of Chicago in William Irvine's lab, where they replaced the starfish embryos by colloids, right? So instead of needing all of the complicated biology that makes a starfish embryo rotate around in a fluid, they use a magnetic particle, right? This is a magnetic dipole. It's a cubic particle, in fact, that has a magnetic dipole in the plane, and they put a magnetic field in this plane and begin to rotate the magnetic field. Then largely the physics is the same. It turns out that these colloids also form crystals that are now much larger. You can make millions of colloids in the plane in 2 dimensions instead of sort of hundreds of starfish embryos. And again, by imaging the system, looking at the deformations of this crystal, you can back out the odd elastic modulus in that case as well. And the final system that I wanted to tell you about is from the Coulet lab at the University of Amsterdam, where they showed that maybe one common ingredient in these 2 previous systems, that these are based on rotating particles, isn't really necessary, right? The real essential ingredient is non-reciprocity rather than rotation. And so what they do instead is to replace the interaction between these kind of vortices, the purely physical interaction, by an interaction that's programmed into a robotic system. Right? So they have a system of robotic actuators. The kind of simplest unit of it is this one, where you have two actuators that exert torques on these 2 angles, and they exert torques in a non-reciprocal way. Right? So what I mean is that you can program in this actuator to sense this angle, right, theta. I'll call this theta 1, and exert a torque here that's a function of theta 1 on this angle. But you can also program this actuator to not have a torque that depends on theta 2. Right? So this is there. In general, they can be not equal, and in particular, this could be set to 0. So in this system in particular, nothing is rotating, but clearly it's breaking some sort of rule of reciprocity. It turns out to be also breaking Newton's 3rd law. So although the kind of microscopic model is somewhat different than this non-reciprocal spring, just purely from a kind of convenience of implementation point, when you make a lattice out of these non-reciprocal torsional springs, you will also recover an odd elastic modulus, and both the wave-like phenomena and the static phenomena associated with it. So rather than kind of go into more details about these models or all of these different systems, I thought I would use sort of the remaining parts of the talk to sort of maybe speculate about what are the interesting themes in active solids, themes that kind of span across different fields, and I welcome kind of your input where you also see this arising in many-body quantum optics. So one theme that I already mentioned is non-reciprocity, and I think one of the challenges maybe in the field of non-reciprocity is the fact that it could mean a lot of different things, right? I already mentioned non-reciprocity as non-reciprocity between action and reaction, but there are other non-reciprocities that are connected to it, perhaps. So perhaps some of the questions.
Like a signal of activity?
In this case, it is, right? I don't think that's maybe, well, maybe it's not always this is, related to activity, but when non-reciprocity specifically means the breaking Newton's law that tells you about momentum conservation, then activity seems like a kind of natural way towards that. Maybe one question that often arises in active matter is sort of, is this a general feature of all active solids in some way, right? I talked about non-reciprocity between action and reaction, but you can define non-reciprocity between two general fields, two general degrees of freedom, and you often, the kind of field theories you write for active matter and for other non-equilibrium systems can be thought of as non-reciprocally interacting fields, right? So the generality perhaps of non-reciprocity and the kind of the general theory that describes non-reciprocal systems are all sort of things that are of interest to me personally, at least. The other theme that I haven't touched upon very much, although I think the question about fluctuations is a very good and related one, is the question of disorder. So all of the models that I presented to you rely on a perfectly kind of structured periodic lattice. Biological systems would never behave in this way, right? Nevertheless, it seems like there are connections between biological systems and these perfectly periodic models are probably connections with other kind of synthetic systems that include disorder either built in or that cannot be made into a perfect lattice. So the question of how disorder changes the properties of active solids, I think, is an open one. And so maybe finally, what is perhaps an interesting thing to discuss is what a quantum active solid might look like, right? How can quantum phenomena arise in models like these, right? That the models that I showed you are purely classical one. How can they be implemented in both optical systems or more generally in quantum systems? And how are, I guess, quantum phenomena both similar and different, that they're sort of classical non-equilibrium counterparts. So maybe should I conclude here, and maybe if there are more questions.
So I suspect I'm not the only one in this audience who has a bit of trouble giving up on momentum conservation. And isn't somehow the question of actually how to reconcile this non-reciprocity with the third law? And so at least in my understanding, typically it happens when there is some sort of a cascade, transfer from small scales to large scale. For example, in, I don't know if turbulence qualifies as, active matter phenomenon, but so if it is forced by, let's talk 2D, forced by on small scales with all stirs, right, there is entropy cascade, i.e. a cascade of vorticity injected on small scales into large scales, right? And the angular momentum is perfectly conserved because on large scales, friction
this is in 2D, ultimately dominates, takes it up, or some interaction with the boundary, right? So, you know, suddenly your chiral little sort of early on sort of coherent rotation and monkey business with angular momentum most certainly falls into that category where a very interesting question is this angular momentum flux, for example. But some of these other stories here are, at least to me, more mysterious in that way.
So I fully agree with you that I think it's a great question and maybe just as general of a theme of how to reconcile you know, the fact that we know that Newton's law works in all of these systems with the fact that it, you know, appears to be violated in some sort of restricted sense. And I think the answer to this reconciliation is always some sort of a hidden degree of freedom, right, which we're kind of used to doing in physics, right? So say that these are kind of the relevant degrees of freedom, like the displacements of the particles, and then, you know, the let's say, momentum of the substrate on which these particles are, or the fluid in which they're immersed, becomes, you know, a non-relevant degree of freedom. And if you were to consider it, maybe you'd have either a more general theory of active solid or some sort of general way of deriving where these kind of non-reciprocal forces come from, like you say, in, you know, by looking at fluid mechanics. So I can give you maybe a very concrete example here, right, in these systems of rotating particles that form crystals. They are always rotating in fluid, and the fluid really, if you take into account the momentum of the fluid plus the particles, then the momentum should be conserved. But somehow, in that case, you can ignore the fluid and get an effective interaction between the particles that appears to be non-reciprocal. There's nothing turbulent here only because they're so small. If you make it larger, it would be turbulent and probably would be also very interesting from that perspective.
So I guess what I gather from that is that there is probably hidden degrees of freedom become relevant on large scale. And on a smaller scale, you can ignore that and just sort of focus on local correlations between neighbors or little regions, but ignore. There's also presumably some time scale involved in this.
No, I think these are all excellent questions. So I think I would say sometimes that, yeah, you might develop a microscopic model that doesn't apply to the macro scale, and in that case, I would say you have to go back and understand where your microscopic model has gone wrong. Where did you discard something that turned out to be relevant? Yeah.
So we, about the same time, every time I hear the word violation of the use of it's just like intrinsically, it's something. It makes me. So I want to bring another example, the example of the falling cat problem, because that's something from my time as a PhD student and a postdoc, where people were thinking, okay, yeah, the falling cat is, you know, you drop it upside down with the feet up, and it just, without any external moments acting on the entire body, it manages to rotate at zero external torque and land on its feet. And that was like a big puzzle. Is it violating the third law? And the answer is that there are internal shape changes. It's a geometric phase because you allow for activity, as you call here, and internal shape changes. And you can use the classic theory of mechanics to explain this phase that happens that causes the rotation, the overall rotation. So what's the link between what you're telling us here about this non-reciprocity and maybe these classic problems that we kind of have some understanding of by now?
Yeah, that's a very good question. I think there are probably lots of links. I guess one way I would say that perhaps some of these active solids models extend the kind of the falling cat problem is that they look at, you know, the many cat problem, right? If you had, you know, Avogadro's number of falling cats, how would that be? How would it be different?
Yeah, it's a short question, but it's more terminological, because when we call it quantum active solid, kind of immediate reaction is that on some level everything is quantum, right?
Yeah.
So then in this way, it's kind of hierarchical, right? So is the terminology that call it quantum, it should be some kind of more certain features, right, which you have in mind, right?
Yeah, I think more the quantum phenomenology of active solids, right, or somehow cases where both the activity and the quantum fluctuations are simultaneously important, right?
You mentioned that within the field of active solids, people are also looking at metamaterials.
Yeah.
Can you explain more the connection, like where the word active kind of enters into the metamaterial?
Oh, yeah. So this, I didn't really define what a metamaterial is, but generally it refers to a material whose properties arise from scales that are much larger than atomic or molecular, right? So you have some sort of a structure some sort of geometry, and the elasticity, the mechanics of the material is based on this geometry rather than its chemical composition. So an example of an active mechanical metamaterial is precisely this kind of robotic metamaterial that I explained at the end, where you take a lattice, right, that would have a certain mechanical properties. Those mechanical properties are based on this, large scale, kind of centimeter scale structure, and you add then motors into this lattice. And now the kind of emergent mechanics is emergent not only from the geometry, but also from these active components. And sort of that's how I would define loosely an active mechanical metamaterial.
So in optics, in like quantum optics, people use non-reciprocity in slightly a different way. But there's been like a lively debate as to what the minimum ingredients are that you need for non-reciprocity. So do you need time reversal symmetry breaking? Do you need external modulation? Is nonlinearity and inversion symmetry breaking enough? Is there a similar discussion, argument, understanding that we can borrow from active solids?
Unfortunately, I'm not sure if I can give you any sort of understanding, but I would certainly agree that there is also an ongoing discussion. I would say that what I can say is that in some cases, there are modifiers to the term non-reciprocity that make it precise, right? But without those modifiers, there are cases that, for example, cases that only rely on nonlinearity, so the non-reciprocity in terms of what's called Maxwell-Betty reciprocity of linear elasticity, right? That could be violated simply by going to a nonlinear elasticity, but that's not the same thing as having an active solid. So I think it's a kind of broad umbrella term for us as well, and it would be maybe useful to kind of agree, if we can, on what it means.
Yes. Yeah, I just a bit confused about why the question mark for the last one, the quantum active solid. So why isn't it like behind you this system from Erlang's lab where you just have these dipoles? Why not just make them small enough that they have quantum fluctuations? And why is that not a quantum active solid?
Well, I'm not sure if I'm an expert on quantum active solids, since I've, written it down with a question mark. I would say that would be really interesting. I think nobody has done it, at least as far as I know, both in terms of doing the experiments or kind of trying to model it. I think in part because perhaps the approach to kind of active matter in classical physics and kind of far from equilibrium matter in quantum physics has been somewhat different, but I think there's probably a lot to be learned from those two.
Yes, Maria.
Thank you very much. I have one of the interests that we have in our program is trying to understand numerical methods or methodologies that allow us to solve for large many-body systems. So typically, mean field theories, when mean field theories work, then we are all happy. On the other one hand, we want to go beyond. So my question is, in all the problems that you solve, are typically mean field-like, or you have to deal with complexities that you have a simple mean field model doesn't work and you have to include for fluctuations and
Yes, that's a great question. I think we have many of the same challenges in our field as well. So I think there has been both a good amount of kind of mean field theories that describe real physical systems that we've encountered, but also cases where you say, fluctuations seem to play a crucial role, or where we don't really know how to even construct a field theory. We have a particle-based model that people know how to simulate very well, but we don't really have a field-like description.
And you have to use some type of master equation as well, or you can deal with more Hamiltonian type
certainly people have used master equation approaches. Sometimes we could, in some cases, right, like in non-Hermitian quantum mechanics, in classical mechanics as well, you can kind of reduce things to a, just a non-Hermitian Hamiltonian-like structure, or, a non-Hermitian dynamical matrix, as you might expect for a solid, but not in all cases. And again, sometimes we don't even quite have the right language yet to even map it onto those.
Okay, so you think the topic of how to go beyond mean field is something that is common for?
Yes, I think it's certainly something that's very open and very interesting.
Okay.
Are there strong links with? I'm wondering if there's strong links with like magnetohydrodynamics that people do. Just take two charged particles, the force that one field's generated by the field from the other one, those are non-reciprocal, and the field, the E and B fields carry away the hidden momentum. So those are non-reciprocal systems, I guess, and people have studied their dynamics for a long time. I guess they're purely dissipative rather than with energy being pumped in. But is that, how strong are the?
I think there are some links. I think we could also, imagine pumping in electric and energy through electric and magnetic fields as well, and that'll make it closer to this. I would say that often our approaches have been sort of minimal, and in those cases, the full kind of magnetohydrodynamics is too complex for us to really make contact with. But certain cases, right, certain very simple geometries, say magnetohydrodynamics, have certainly been useful, and I can give you some examples if you like.
Okay, let's thank